Okay, combustion stoichiometry questions. They range from being pretty simple, pretty straightforward, to being quite challenging. So these are going through the 3 practice questions in the notebook packet. So the place to begin is to actually start with the products. You're being asked about the empirical formula of the hydrocarbon, which is what you're combusting, so it's a reactant, but actually you can use the information about the products and the mole ratios that we know about complete combustion to work out the empirical formula of the hydrocarbon. So you start out with your 3.6 grams of water, 18 grams per mole, and you get 0.2 moles of water. You do the same thing with the mass of CO2, divide by the molar mass of CO2, 44, and you get 0.2 moles of CO2. Well, because every water has 2 hydrogens in it, if you have 0.2 moles of water, that's 0.4 moles of hydrogen. And since every carbon dioxide has 1 carbon in it, if you have 0.2 moles of carbon dioxide, then you have 0.2 moles of carbon. And so from here, the carbon and the hydrogen, since we know from combustion that all of the carbon ends up in CO2 and all of the hydrogen in our fuel ends up in water, once we've used the water and the CO2 to get the moles of H and C, then we basically have the empirical formula. I can see that there's twice as much H here as there is carbon, and therefore the empirical formula is CH2. The molar mass is 56, and a little review from topic 1. This empirical formula weighs 14 because of the 1 carbon and 2 hydrogens. So how many times bigger is 56 than 14? Well, it's 4 times bigger. So the actual molecular formula is C4H8. Okay, question 2 is a bit different in how it's presented. It's actually a reminder of the topic of Avogadro's law, which says that for gases, volumes are proportional to particles, number of particles, which means number of moles. So when they tell us that 150 cm cubed of your unknown hydrocarbon, so your starting fuel, is completely combusted, and it gives you 450 cm cubed of CO2, and it gives you 600 cm cubed of steam. I think at first that really throws people off, but the key thing to remember is just the ratio. Sorry about that. The ratio is what matters. So really, it's telling us that 1 volume of the hydrocarbon makes 3 times as much CO2 and makes 4 times as much water. So what I'm looking at here is what's the ratio of 150 to 450, right? And so the thing to remember is that chemical equations follow ratios. And so just because in this example they used 150 cm cubed and 450 cm cubed, I can pull from that the ratio that it's 1 is making 3. For every 1 hydrocarbon, I'm making 3 CO2s. For every 1 hydrocarbon, I'm making 4 H2Os, because 150 to 600 is a 1 to 4 ratio. So I can see now that since 1 hydrocarbon made 3 CO2s, where did those 3 C's come from? If I have 3 CO2s, then that's like having 3 carbons. That means in the initial hydrocarbon, there must have been 3 carbons relative to the amount of carbon dioxide. And if over here I have 4 waters, I can see that 4 times the 2, that means there are 8 hydrogens. And so in the original compound, there must have been 8 hydrogens. So that ends up being the empirical formula of the hydrocarbon. So we can use these volume ratios. The volume ratios for gases are just like the mole ratios. They are proportional to one another. So we simplify down the ratio and we think of it as moles. We get 1 to 3 to 4. And then we work out what that means for the number of carbons and hydrogens that are in the 1 hydrocarbon. I find that one gives people more trouble. Conceptually, I think it's a little bit more challenging to think through, but it's a good review of Avogadro's law. Okay, the last one, and by far the most tricky of the stoichiometry problems. So it kind of starts the same. You've got your mass of carbon dioxide and you've got your mass of water, and the first thing to do is just to convert them both into moles, so we can figure out about the moles of carbon and the moles of H. Okay, let me grab the calculator here. Okay, 5.94 divided by 18 is, 5.94 divided by 18 is 0.33 moles of water, which means 0.66 moles of H. I do the same thing down here with carbon dioxide. I get 0.22 moles of CO2, which means 0.22 moles of carbon. Okay, now the trick with this one, if we go back, I kind of skipped over reading the question. 5.06 grams of compound X, which contains carbon, hydrogen, and oxygen, is burned completely. So sometimes our fuels contain carbon and hydrogen, but they also contain oxygen. Now, what makes this so tricky is that combustion is a reaction with oxygen. And so in the end, when I make CO2 and I make water, unlike carbon and hydrogen, where I know that all of the carbon came from the fuel and all of the hydrogen in water came from the fuel, I can't say the same for oxygen. Some of the oxygen comes from the O2 that we're burning with, and some of it comes from the fuel itself. That's what makes this problem so tricky. So the way that I approach this is I do know that the original compound weighs 5.06 grams. That's the original mass that I have. Well, now that I know the moles of hydrogen and the moles of carbon, I can figure out how heavy those are. So 0.66 moles of hydrogen is basically 0.66 grams, since it has a molar mass of 1 if we're rounding off. And carbon, 0.22 moles times 12 is 2.64 grams of carbon. And so I know that the carbon and the hydrogen together is 2.64 grams plus 0.66 grams, and that is 3.3 grams due to the C and the H. Well, if I subtract that from 5.06, then I can tell that 1.76 grams must come from oxygen. So again, I was told I have this many grams of the compound, and I've determined from my previous calculations that 0.33 of it is the carbon and the hydrogen. So that just means that the remaining mass out of that 5.06 grams must be from oxygen. I can then turn that into moles, divided by the molar mass of oxygen. I get 0.11 moles of oxygen, and now I can get an empirical formula. Now, I'm actually solving question B first. Sometimes you'll get this. The IB will occasionally present you with a question where actually it might be easier to approach the second part instead of the first part. We could actually do this in either order, but I've chosen to do it this way. So let me finish this off and then we'll figure out the percent composition. Okay, I now have moles of oxygen, carbon, and hydrogen. When I have one with 3 different elements, it's best to always divide by the smallest one. So I've got 0.22 carbon to 0.11 oxygen. That's a 2-to-1 ratio of carbon to oxygen. I've got 0.66 H to the 0.11 oxygen, and I've got a 6-to-1 ratio of hydrogen to oxygen. So for the same 1 oxygen, I have 2 carbons and 6 hydrogens and 1 oxygen. So that's the empirical formula. Now, in terms of percent composition is percent by mass. I have the 3 component masses now. I have that the compound contained 0.66 grams of hydrogen, 2.64 grams of carbon, and 1.76 grams of oxygen. So when I got to that point in the question, I could have focused on the percent composition question, but I was kind of wanting to get towards that empirical formula. So now I can go back and I would just divide each by the mass of the whole thing. So this is the mass of hydrogen, and I multiply it by 100 to make it a percent. So 0.66 divided by 5.06, the compound is about 13% hydrogen. The 2.64 grams divided by 5.06, the compound is about 52.2% carbon, and therefore I can see that the compound must be about 34.8% oxygen. So that's the percent composition of the compound. So once you know the mass of each part, you can divide each part by the whole mass and get the percent composition. The last question tells us the molar mass is 46. When I add up this mass is 46, and therefore if the molar mass is ever the same as the mass of the empirical formula, then the empirical formula is also the molecular formula. So we actually don't need to make a change at all. They just happen to be the same in this case. So this one is really challenging because the compound has oxygen in it. It provides all sorts of extra hurdles that we have to jump through. It also asks you to calculate percent composition on top of empirical formula. You know, is this question common? Not at all, but it is something they could throw at you every now and then as a real strong challenge. So just remember to start with the carbon dioxide and the water grams, convert those into moles to know about the moles of carbon and hydrogen, and then from there, use your problem-solving skills, know that you can turn moles into grams, and if you can figure out the mass of each part, you can determine both percent composition and empirical formulas.